Welcome to The Explainer. Today we're going to do something a little different. Think of it like an architectural tour of the entire animal kingdom. We're going to uncover the surprisingly simple blueprints nature used to build everything, from a jellyfish all the way up to, say, a jaguar.
So, how do you build an animal? I mean, with millions of species out there, you'd think the answer has to be ridiculously complex, right? But here's the cool part. Evolution is, well, it's kind of a master recycler. It's been using the same small set of core designs again and again and again.
So is there a secret formula? Oh yeah, for sure. There are these fundamental blueprints that connect critters that seem totally unrelated. And stick with me, because by the end of this, you're going to see the animal kingdom in a whole new light. Not just some random list of animals, but this beautifully logical family tree based on design.
All right, let's dive right in. Blueprint number 1, building with layers. This is the first, most fundamental choice you have to make when you're designing an animal. I want you to imagine for a second that you're evolution. The very first question on your checklist is, okay, how many layers of tissue is this thing going to have?
And it turns out there are really only two answers. You can go simple with 2 layers, biologists call that diploblastic, or you can level up and go for 3 layers, the triploblastic plan. And let me tell you, that third layer, well, that's where things get really interesting.
Okay, so let's start with the simple one, diploblastic. The easiest way to think about it is like a sac inside another sac. You've got an outer layer, the ectoderm, that's basically the skin, and an inner layer, the endoderm, which becomes the gut. And that's it. That's all you need to build a jellyfish or a sea anemone. It's a super simple, super efficient design for a pretty simple life.
And this diagram of a sea anemone shows it perfectly. See that? You've got the outer skin and the inner layer that lines the gut. And that jelly-like stuff in the middle? That's called the mesoglia. It gives it a bit of structure, but it's not a real tissue layer. It's a minimalist design. And hey, for a lot of animals, it works just fine.
But if you want to build something more complex, evolution came up with a massive upgrade. A third layer, the mesoderm, squeezed right in between the other two. This is the triploblastic plan, and it's the foundation for, well, pretty much every other animal you can think of, from a tiny worm all the way to us.
And this middle layer, this mesoderm, is an absolute game changer. Seriously, think of it like the body's general contractor or construction crew. It's the raw material you need to build all the cool stuff. Real muscles, bones, a circulatory system, all the complex internal organs that make advanced life possible.
Okay, so now that we've got our third layer, a whole new problem pops up. It's great that you can build all these amazing new organs, but where are you going to put them all?
Exactly. You need a room for your organs. You need some kind of internal space for everything to fit into, a body cavity that can house and protect and support all that delicate internal machinery. And figuring that out was the next great evolutionary puzzle.
And evolution, being evolution, didn't just find one solution. Nope, it came up with 3. And this split the triploblastic animals into 3 major groups: the ones with no cavity at all, the ones with a kind of fake cavity, and the ones with a true body cavity.
So first up, the acoelommates. That A at the beginning just means without, and colome means cavity, so without a cavity. Simple enough. If we look at our flatworm buddy again, you can see it's just solid tissue. The mesoderm packs the entire space between the gut and the body wall. There's no room in there for anything to slosh around.
All right, next we've got the pseudocoelomates. Take this roundworm, for example. It does have a fluid-filled cavity, which is a big step up. It gives the organs some space, and the fluid pressure even helps the animal move and keep its shape. That's called a hydrostatic skeleton. But here's the catch. We call it a pseudo, or false cavity, because it's not fully lined by that all-important mesoderm tissue.
And that brings us to the final and most advanced plan, the coelomate. This is the blueprint for us, for this earthworm here, for most of the animals we know. In this design, you get a true body cavity, a column, that is completely wrapped up in mesoderm. And this is just a brilliant setup. It means your organs can be suspended by membranes, giving them tons of room to grow and move around without bumping into the body wall.
Okay, quick recap. We've got our layers sorted out, we've got a plan for a body cavity, but there is one more brilliant trick up evolution's sleeve. One final innovation that really unlocked the door to building big, complex, and super adaptable animals.
I personally call this the Lego principle. Think about it.
Instead of trying to design a super complex animal all in one go, from scratch, why not build it out of a bunch of repeating modular parts? It's way more efficient, way more versatile. Just like building something amazing with a pile of Lego bricks.
The official biological term for this is metameric segmentation, and the genius of it is that each segment can start out as a basic copy, but then they can specialize. You could have a few segments turn into legs for walking, a few others could become gills for breathing, maybe some up front become antennae for sensing. It's an absolutely revolutionary design that gives you just incredible flexibility.
And what's so wild is that you can see this exact same principle at work in animals that look nothing alike. On the left, you've got a leech. It's a type of worm. On the right, a trilobite, an ancient arthropod. They're both built from a series of repeating segments. But evolution has just tweaked and modified those segments to build two totally different machines, each perfectly suited for its own way of life.
So, let's put it all together. What's the big takeaway here? How do these three relatively simple ideas, layers, cavities, and segments, create the absolute explosion of diversity we see in the animal kingdom?
Well, it really just comes down to mixing and matching. It's all about the combinations. With these three core principles, evolution suddenly has this massive toolkit to play with. You can be three-layered, have a true column, and be segmented, boom, you get an earthworm. Or you could be three-layered, have a false column, and have no segments, and you get a roundworm. Each combination is like a whole new path for life to go down.
And once you grasp this framework, it's really powerful. It helps you see the logic, the hidden family connections between animals that seem totally different. Suddenly, a lobster and a centipede don't seem so random. They start to look like cousins. The whole animal kingdom stops being this overwhelming list of names and becomes this logical, interconnected story about design and innovation.
And that, I think, is the real beauty of it all. It's a great reminder that even when you're looking at the most mind-boggling complexity in nature, underneath it all, there are usually just a few simple, elegant rules at work. The blueprints are there, but evolution, it's never done building. It's always innovating. Which leaves us with the big question, right? What's it going to design next?